In this video, we're going to talk about shifting juggling states. A juggling state is a snapshot of where the balls are in a pattern at a particular moment in time. We're going to talk about what a state is, how we move between states, and then we're going to generalize that movement between states to get a really surprising ending. I'm going to start off with a clip of myself juggling, and you have a very simple task of telling me what the colors of the balls are. Here we go. So, what are the colors of the balls in the order in which they are thrown? I'm sorry, I haven't really gotten a good hang of this whole animation thing here. The question should have been complete before I showed the video. But to be fair, at full speed, it's really hard to answer this question. So what I'm going to do is I'm going to show the same clip in slow motion. I will call out the colors of the balls as they are thrown, and I'll also flash the colors on the screen. Pay attention to the hands to keep me honest. Here we go. Blue, green, red, orange, orange, blue, green, red, red, orange, blue, green, green, red, orange, blue, blue, green. Now you might have noticed that we alternated through the colors blue, green, red, orange, every once in a while repeating a color. As a mathematician, I would say, hey, that's a curious little pattern there. How could I study it? Well, I could list out the colors kind of like I did on the screen, but I think it's better to just put a bunch of dots down and color the dots according to the color of the ball that was thrown. So the very first time I threw a ball, it was blue. I'm going to say that I threw that at the first beat. A beat is sort of the time unit of juggling. At the second beat, I threw the green ball. At the third, I threw the red, and so forth. Another mathematician might look at this and say, oh, it looks like he's about to draw a graph. This isn't the type of graph that you drew in high school where you'd plot a bunch of points, connect the lines, and get a pretty curve. This is a graph that consists of vertices and edges. The vertices are the dots that we've drawn. One dot is called a vertex, and an edge is a connector between two vertices if they share some property. We're going to draw an edge between two vertices if they have the same color and they're consecutive among all vertices of that color. So we'll connect the first blue to the second, this first green to the second green, the first red to the second red, and the first orange to the second orange. Then we connect the second orange to the third, the second blue to the third, and so forth. What we have here is what's called the juggling graph for this particular pattern. There are different ways we can draw it. This particular rendition is nice because we can see that it's a 4-ball pattern because there are 4 different colors. But other renditions might not really reveal that. So let's go ahead and show you another way you can get the number of balls. To do that, I want to separate it into 4 separate graphs according to the color. And I want you to notice that in each color, the very first vertex looks kind of different than the rest of the vertices when you look up close. Notice that the first blue vertex has only one edge touching it, and it's going off to the right. Any other vertex, let's say the one there in the middle, has an edge coming in from the left and an edge going out on the right. Why the difference? Well, the one in the middle, the edge coming in from the left, represents the fact that there's a ball in the air, the blue one, that's about to be caught. It gets caught, that's kind of the representation of the vertex, and then it gets thrown back into the pattern. That's what the right edge is telling us. Why does the first vertex not have that? Well, the first vertex doesn't have the one on the left because the ball's not in the air yet. So we're introducing the ball into the pattern. If I can determine how many vertices have that particular behavior where I'm introducing a ball into the pattern, that will tell me the number of balls. This is really handy because if I had been juggling black balls instead, the graph would look like this. There's no color to it. And to determine the number of balls, we just need to find the places where we have an edge going off to the right, but not one coming off from the left. That is these 4 highlighted vertices. Below each of these vertices, we're going to put a 1 to represent that we need to add 1 ball to the pattern there. Anytime we don't need to add a ball to the pattern, that is, when we have an edge coming in from the left and an edge going out from the right, we're going to put a 0. And that is how we get our state for this particular pattern. We'll just call this the state 1111 because we just say, oh, I am going to assume that there are zeros that follow that forever. Remember that the first ball that I threw was the blue one. Had I started 1 beat later in the juggling pattern, remember a beat is sort of the time unit of juggling. Had I started 1 beat later, this is the graph I would have obtained. That would be if I had started with the green ball. Notice that at the fourth vertex, we have an edge coming in from the left and an edge going out on the right. That deserves a 0. The vertices beforehand all only have ones going out to the right, and the vertex immediately after that 0 only has one going out to the right. So this would be a different state. It would be the state 11101. Had we started with the red ball instead, the third throw, we would get 11011, and had we started with the fourth throw, the orange ball, it would be 10111. It turns out that if you continue to look down the pattern, starting one beat later, you're going to cycle through those 4 different states. For this reason, we say this is a juggling pattern of period 4. The period is the number of states that we cycle through. Now I want to first of all confess a little mistake that I made before, and then show you another way to get the state. I said that this was a graph, and a mathematician might say, no, it's not. Look at the 4 little edges, kind of like spider legs hanging off at the right side there. A mathematician would say it's not a graph because whenever you have an edge, it has to have a vertex at each endpoint. And those 4 little spider legs do not have vertices at those endpoints. And I confess, that's true. What I really wanted to do was give the impression that this was going to continue on forever. But for sake of argument here, and for sake of interpreting the state another way, I'm going to put some vertices there. I'm going to color them blue, though, because they're going to be a little bit different. What I've done here is I've drawn 5 periods of the juggling pattern. I want a whole number of periods, and I want a number of periods so that all of the balls are in the air, and that's the case here. And what I want to do is I want to imagine stopping immediately after that 5th period, and then listen to the balls as they land in my hands. I'm not going to throw them back into the pattern anymore. Those are the 4 blue vertices. And notice they go plop, 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 plop. 4 immediate catches. Remember that the state of this particular juggling pattern was 1111. The landing schedule, as we call it, will also be 1111 if we're counting the places when we catch the balls and don't throw them back into the pattern. So this provides another interpretation, the landing schedule, and the landing schedule is going to be a better interpretation later on in the video. To get the landing schedule, here's what we could do. We could go through a whole number of periods, sort of stop, and that's what this dotted line indicates. We notice that that dotted line intersects 4 different edges, and we just need to find out when those edges land. So I'm going to show you how we can do this in a more efficient manner. Take any juggling graph where we've gotten all the balls into the air, stop after a whole number of periods. So on the very left here, this is immediately after a whole number of periods have been stopped. Now imagine 4 consecutive dotted lines here and look at where they intersect. I'm only going to draw their intersection points, and I'm going to represent them by the colors of the balls where they intersect. Here we have it. Okay, so at the first intersection point, look at the first red vertex. It moves to that one, and to that one. It is 3 beats before that ball is caught, so I'm going to note a 3. The green one, however, only has 2 beats before it will be caught, so we're going to represent the blue dot or the green dot there with a 2. And then the orange one, well, you can count that's 4 beats, and the blue one is 1 beat. Okay, we're going to do something with this in a little bit. But let's practice again with the next set of 4. The orange is going to land in 3 beats, the red in 2 beats, the green in 1 beat, and now the blue will land in 5 beats because it's been launched back into the air. If we do the same thing with the next 2, and the reason we're doing 4 is because this is a juggling pattern of period 4, those are the numbers that we'll get if we do it with the next 2. Now, what does this have to do with the states? Well, let's bring the states back onto the stage. Here we go. And notice that in the first column of numbers, we had 3, 2, 4, and 1. Well, notice that those are exactly the positions of the ones in the state. In the second column, we had 3, 2, 1, and 5. Those are where the ones are in the next state, and 1, 2, 4, and 5 in the next, and 1, 3, 4, and 5 in the next. So this provides a way of determining the states as we cycle through them without having to draw a whole bunch of different graphs. So it's a nice little thing. Let's look at where the orange dots are. In the first state, it's in position 4. In the second state, it's in position 3, then in position 2, then in position 1. Why does it cascade down those numbers? Well, in the first state, the fact that the 1 is in position 4 indicates that the orange ball is going to be caught in 4 beats. Then 1 beat passes, and we're now in state 11105, the second state. So that orange ball that was going to be caught in 4 beats, after 1 beat, will only be in the air for 3 more beats. And then when we move to the next one, it's only in the air for 2 beats, and so forth. So you'll have this little diagonal of orange ones, if you will, going that way. Similarly, the red ones, the first red one is in the 3rd position, in the next state it's in the 2nd position, and then in the 1st position. The same thing is true of the blues and of the greens. And so we'll call this the shifting state rule, which says that if we have one state, we'll call it state B, and it follows state A, and state A has a 1 in position 2, then state B must have a 1 in position 1. It has to have shifted 1 spot to the left. If state A has a 1 in position 3, then state B would have to have a 1 in position 2. Let's call the 3rd state state B, for example, and the 2nd state state A. Notice that in state A, the red 1 is in position 2. In state B, the red 1 is in position 1. In state A, the orange 1 is in position 3. In state B, the orange 1 is in position 2. That's going to be a rule for us to know whether or not one can follow another. We'll call that a necessary condition. The shifting state rule is a necessary condition for one state to be able to follow another. You might want to think about a parent telling their child, if you want to go to the party tonight, you must clean your room. That's a necessary condition. Well, the child goes and cleans the room, and they come out and they say, okay, my room's clean, I can go. And the parent said, no, 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 you also have to take out the garbage. And the child says, okay, wait a minute. I've got to barter with my parent at this point. Okay, if I take out the garbage and if I clean my room, can I then go to the party? The parent would say yes, and so that becomes a sufficient condition. It's enough for you to take out the garbage and clean your room in order for you to go to the party. And so the shifting state rule will also be a sufficient condition provided the 2 states have an equal number of 1s. Let's look at a way to represent the transition between states in a graphic manner. What I've done is I've put all of my states along the bottom, and I've put all my states along the left side as well, to help us understand when we can transition from one state to another. The ones along the bottom are going to be what we call our initial state. That's the state we're starting from. And the ones along the left side are going to be the terminal state. Those are the ones we're ending at. Let's take a particular state. Let's look at the state 11101. Where are the ones in it? They are in positions 1, 2, 3, and 5. The one in position 1 does not really do much for us because that ball is going to be caught and then thrown back into the pattern. It's the ones in positions 2, 3, and 5 that are important. Because they're in 2, 3, and 5, if a state follows this particular state, they'll shift 1 spot to the left and be in positions 1, 2, and 4. So we need to look along the left-hand column and see which of those states match that. Well, that would be state 1111 and 11011. So what we're going to do is identify those two, and then we'll place a square in those particular grids next to those states that can follow. If we do that with all of them, this is the graph that we get. You might notice a new state in here, 0, 1, 1, 1, 1. Why did I include that? I included that because all of these states correspond to throws that are in the air for 5 or fewer beats. So it's a pretty condensed little graph there. If I include states where we can make throws that are in the air for 6 beats or fewer, the graph gets a little bit more robust. There's a little bit more options. So it's kind of a nice, pretty graph there. Now you might wonder, how did you decide the order in which to list the states? I started with 1, 1, 1, 1 at the bottom and worked my way up. You might notice that they're getting longer as we move up, for one thing. But there's another way to determine which one is before another. Let's take the state 1111. What we're going to do is we're going to multiply each of these numbers in a state by a power of 2. The number at the leftmost we're going to multiply by 2 to the 0th. Remember that 2 to the 0th is equal to 1. Then we're going to multiply the next one by 2 to the 1st, the next one by 2 squared, the next one by 2 cubed, and so forth. So to the state 1111, we're going to associate the number 15 because that is 1 times 2 to the 0th plus 1 times 2 to the 1st plus 1 times 2 squared plus 1 times 2 cubed. Notice that the highlighted coefficients of the powers of 2 are 1, 1, 1, and 1, the numbers in the state. Let's look at the state 1, 1, 1, 0, 1. Well, that's going to correspond to the number 23 because the coefficients of the power of 2, look again at the yellow numbers, go 1, 1, 1, 0, 1. They match the ones and zeros in the state. If I had looked at the state 1, 0, 1, 0, 1, 1, that's going to correspond to the number 53. Again, the coefficients go 1, 0, 1, 0, 1, 1. Along the bottom, we're going to rank the numbers from smallest to largest. Along the left-hand side, we're going to rank the numbers from largest to smallest. Now I want to generalize things a little bit. Remember the graph where I said, okay, let's stop juggling and see what happens? Let's look at those last 4 beats and see what happens with the states there. Right at the very beginning of that, we still have 4 balls in the air, and they're going to land in 3, 2, 4, and 1 beats, and so that would correspond to the state 1, 1, 1, 1. But then I catch the blue one, and I don't throw it back into the pattern, leaving only the orange, red, and green balls in the air. The orange is going to be in the air for 3 beats, the red for 2, and the green for 1. So that would correspond to the state 1, 1, 1. Then the green ball is caught not thrown back in. That leaves us with the state 1, 1 for orange and red, and then that leaves us with state 1 when only the orange ball is in the air. Notice that the shifting state rule still applies. If there's a 1 in any position, in the next state, it's going to be 1 spot to the left. You can't magically pull a ball out of the air. The shifting state rule remains a necessary condition for one state to be able to follow another, but this opens up the book just a little bit. It's also a sufficient condition if the 2 states have an equal number of 1s or the second state has 1 fewer 1 than the first state. Now let's look at the other end of the spectrum, when I first started introducing balls into the pattern. Let's go ahead and mark up the graph again to know the colors. First I started with just 1 ball in the air, the blue one, and that would be state 0, 0, 0, 0, 1. Then the green ball gets introduced. The blue ball is now 1 spot to the left. That's going to be 0, 0, 0, 1, 1. Then when the red ball comes in, it's 0, 0, 1, 1, 1. And then when the orange ball comes in, it's 1, 1, 1, 1. Notice that the number of balls is increasing because we're increasing the number of 1s as we go. The shifting state rule still applies. If there's a 1 in position 4 in one state, there will be a 1 in position 3 in the next state. And if I go ahead and add 1 vertex to the left and think about what state that would be, well, there are no balls in the air, so we would call that state 0. So once again, the shifting state rule is a necessary condition. The sufficient condition is either they have the same number of 1s or the number of 1s differs by 1. Let's look to see what would happen with the graph if we were to do something with this. Now we're going to take all of our graphs, the 3-ball graph, the 4-ball graph, the 5-ball graph, and others, and merge them into one. How do we rank the states? We're going to use that rule where we multiply by powers of 2 and add those up. That's how we'll rank them. This is the graph that we'll get. I eliminated the grid lines. At the moment, this has no interaction between the graphs where we have a different number of balls. Let's first add the condition that we can hold on to a ball to take it out of the pattern. You're only going to see a small change right along the bottom. Here we go. There it is. Now let's add the rule that we can introduce 1 ball into the pattern. This is a little bit more interesting. There it is. Now let's take this one more step. Here I am. I have 2 that I'm juggling. At the moment, the state would probably be 0, 0, 0, 1, 1. Let's suppose I have 3 very skilled assistants who can each throw me a ball so that it goes in the appropriate place so that I'm ready to juggle. There they are. That would move us to the state 1, 1, 1, 1, 1. Again, the shifting state rule still applies. If there's a 1 in position 4 in the original state, there will be a 1 in position 3 in the next state. And then we go ahead and start juggling. There you have it. Now we can extend that shifting state rule. Assume any number of balls can be added. The shifting state rule is a necessary and sufficient condition for one state to be able to follow another, and it doesn't matter how many balls we're juggling. We just need to make sure that if there's a 1 in position 5 in one state, in the following state there will be a 1 in position 4, and so forth. It's really exciting to watch the graph develop, so let's do that. What a surprising graph. A mathematician recognizes this as the Sierpinski triangle, but if you're not familiar with it, you can see this nice little structure to the pattern. Let's talk for a moment about the Sierpinski triangle. What you can do to generate it is start off with a nice solid triangle, divide it into fourths, and then remove that middle fourth. So we would have something like that. Then you have now 3 smaller triangles. You can take each of those 3 smaller triangles, divide them into fourths, remove the middle fourth, and you'll end up with 9 little triangles. You could then divide those into fourths, remove the middle fourth, and continue. That's how you can generate the Sierpinski triangle. The Sierpinski triangle comes up in many surprising places. If you're familiar with the puzzle Towers of Hanoi, you can somehow generate something that looks like the Sierpinski triangle there. If you're familiar with Pascal's triangle and color the odd numbers gray and the even numbers white, you'll generate the Sierpinski triangle as well. I want to take a moment to thank you for watching. If you enjoyed what you saw, please subscribe. I have other videos about fun combinatorial types of things, but I do have some other videos on the mathematics of juggling. So if I've piqued your interest there, please watch some of those. So if I've piqued your interest there, I encourage you to watch those as well.